Welcome to the solutions video for the Math 30-1 Unit 6 unit exam. So here we go, permutations and combinations in the binomial theorem. So here, a high school administrator is planning on creating new student identification codes. The members of the team are considering 4 possible plans, all of which do not allow for repeating letters. So we need to choose a plan based on these ID codes. Notice here that we don't have to actually solve it, we just have to say which of these represents the plan. So this is a fundamental counting principle problem. So in each case, right, so plan 1 here, we've got 1 letter, not including I or O, followed by 2 digits. That's 24 letters to choose from, then 10 options and 10 options. So plan 1 is in the second column. Plan 2, any 2 letters except I or O, followed by 1 digit. So notice here, letters are not allowed to repeat, numbers are. So 2 letters, that means we're starting with a 24 and 23, followed by a digit. So plan 2 is the first one. Now any 2 letters, followed by 1 digit, not including 2 or 3, that would be our last plan, or the last pattern here. Because that's the entire alphabet, the one we didn't use, and then the other 2 left. By process of elimination, the third column should be 4, 24, 8, 8. That's any or 1 letter, followed by any 2 digits. So this looks like they forgot the I or O part of that. Okay. Now the number of 3-digit numbers less than 700 that can be created if the last digit is either 4 or 5 is. So 3-digit numbers less than 700. That means we have 6 options for our first digit. Right, the biggest is 699. If it's less than 100, where that leading digit would be 0, then we don't have a 3-digit number, we have a 2-digit number. So we've got 6 options for the first blank, 2 options for the last, and 10 in the middle. So that makes 60. Now, a child has a pail of identical building blocks consisting of 2 black, 4 white, and 6 red. The child decides to stack the blocks to make 1 tall tower. And how many ways can the blocks be stacked in the tower if all the red blocks must be at the top? So we have all 6 red at the top. There's really only one way to make that if the blocks are identical, as it says. So what we're really looking at is how many ways are there to arrange the 2 black and 4 white. Okay, so we could do this with fundamental counting principle. We could also do this with combinations. We could say of those 6 spots in the bottom, we pick 2 to be black. So 6C2 is the same as 6C4, like we're picking the white spots. There's 15 different ways to pick the black, and once we pick the black, the white and red are completely determined. Alternatively, 15 ways to pick the white, and then the black and red are completely determined. Here we want to simplify this following expression. So n minus 1 factorial over n minus 3 factorial. So we can start by expanding our numerator. So here's the pen I'm looking for to make. Stop zooming. To make n minus 1 times n minus 2 times n minus 3 factorial. Those cancel. And from that we're going to subtract the n factorial over n minus 2. So that's n times n minus 1 these n minus 2's cancel out. So we'll be left with n squared minus 3n plus 2 on the left, minus n squared minus n on the right. So that's a negative 3n plus 2 plus n when our n squares cancel. So that's negative 2n plus 2, or the equivalent. And we do have negative 2n plus 2 right there. The starting lineup of a school softball team consists of 4 grade 10 students and 5 grade 11 students. Before the game, the 9 students line up in a row for a photograph. The number of different arrangements, if the grade 11 students all stand together, is given by. So we start by saying we've got 5 arrangements. We've got 4 grade 10 students to arrange, plus all of the grade 11s. So that makes a 5 factorial there. And then we have 5 factorial ways to line up the grade 11s themselves. So that's a 5 factorial, 5 factorial. All right, sorry, and I just realized here, we had the right logic, but I typed in the wrong number. We were correct that there's 6 options in the first blank, and then 10 in the middle and 2 at the end, but I only multiplied the 6 and the 10, not the 2. Right, so how many different ways are there to arrange all the letters in the word Nanuarluk, a word for polar bear, if the arrangement must start with exactly 2 n's? So in other words, we have it, and then at the beginning, we have 1, 2. So of the 2 n's, we have 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 letters aside from the 2 n's. So we have, in principle, you would think it's 8 factorial, except it must start with exactly 2 n's. So our third n cannot be the third letter. So we have 7 options for the third letter, and then 7 factorial when the n is allowed again. So we have to have 7 times 7 factorial right off the bat. The 2 factorial are to account for the 2 a's and the 2 u's. The school plans to send 5 of the students on the student council to a student leadership conference. There are 5 grade 12 students and 10 students. Okay. So if at least 3 grade 12 students have to attend the conference, how many groups of 5 from the student council could be made? So of these 5, we have to choose 3. So 5C3 tells us there's 10 ways to choose the grade 10s. And then we have to choose 2 of the other 5 students. Okay. Okay, actually I think with this extra blank, I think it should be 10 other students. Yes, okay. The word other is missing here. My apologies. There's a gap there that should have the word other. I believe I corrected that before I printed the tests. Hang on. That's not what is missing. So, yeah, that is the issue. But notice it says at least 3. So we should have 10 other students. The word other is missing. So there's 450 ways to send exactly 3 students. If we send 4 of them, that 5C4, there's 5 options there. And there's 1 way to do the 10. So that's 50. And then there is 1 more way to send all of the grade 12s. So we should have the word other in that spot. So to evaluate the expression 12C5, one must simplify. And yes, that going right back to the version on the formula sheet, it's 12 factorial over 5 factorial, 7 factorial. Now, how many 5-card hands from a standard deck of 52 cards have exactly 3 jacks? So we have exactly 3 jacks. We start with 4 C3. So we're picking just the 3 jacks. So there's 4 ways to pick 3 jacks. If it's exactly 3, then that means the other 2 cards in the hand come from the remaining 48 cards in the deck. 48C2 is 1,128. We multiply that by the 4 ways to pick 3 jacks, and we get 4,512. Continuing on to the last 3. One of the terms in this expansion is 324,135x squared. We have to find the numerical value of k. So if we have x squared, that tells us which term we are looking for. So our equation says that the tk plus 1th term is nck, and then in this case we're going to have a 3x to the k. Actually, because k is this term, that was a poor choice of variable. Let's call that m and pretend it was always m. And then here we have a k to the n minus m. In this particular case, we know n is 6. So we have, the term is 324,135x squared. And that 4 that looks like a 9 is all on me. It's not the small lim-noob print. And then x squared. So our m is 2. So we have 6c2 times 3x squared times k to the 6 minus 2. So 324,135x squared, 6c2 is 15 times the 9x squared times a k to the 4. So if we divide both sides by 15 and by 9x squared, 324,115 or 135 divided by 15 and divided by 9 gives us 2,401, and that is our k to the 4th. So it is 7 raised to the exponent 4. That gives 2,401. So our k is 7. So in this expansion, coefficient of x squared y to the 5th is, so of our 8 terms, we are looking for term number 6. So that's where k is 5. So we have a 7c5 times, in this case we're going to have our 3 squared, so times 9, and that works out to 189. And finally, if the number of terms in the expansion of this binomial is 23, then the value of a is, well, the number of terms in this expansion is going to be the exponent plus 1. So if there's 23 terms, this exponent is 22, which means a itself has to be 17. And this concludes the solutions to the Unit 6 exam.